Good morning. So today's lecture we will continue more in the examples that we discussed about linearity, stability, invertibility in LTI systems. Then we will expect to start the impulse response. So today, 29th, Monday, the lead is page 35 to 40. And 31st, which is Wednesday, the readings are page 40 to 50. This is the due date for homework number 3. So problem 2.1. I think you can see the homework details there on Canvas. And on Friday, February the 2nd, the readings from page 40 to 50. Then next week, in February 5th, Monday, it is the due date for homework 4 and also due date for homework 5. But keep in mind that homework 5, no submission. So it's just like homework 4. Homework 5, again, no submission, but it's very important for the first exam. So this is like until homework 5. While, just keep in mind the submission for homework 3 Wednesday, while homework 4 Monday. Okay? Yes?
When's our first test date in the area?
The first test, I think it's already been assigned in Canvas. 14th? Yeah. Yeah. It's been 14th. So it's still early to talk about the test. Any other question? Okay. So keep in mind that the Friday lecture might come maybe late 5 minutes. So just have to skip 5 minutes because I have a meeting before that. It's supposed to end around 10, but in case I late 5 minutes, it should be fine. Just keep in mind. Let's continue the examples. So last lecture we stopped at number 3, which is y of t equal to cosine of x of t. Now we need to check linearity, stability, and invertibility. So how can we do this? Let's, like I used to write A for linearity, check is it linear or not. So the first thing is replace every x by ax1 plus bx2. This yields to cosine of ax1 plus bx2. Now the other thing, y1 number 2 y1 equal cosine of x1, y2 equal cosine of x2. Therefore, a y1 plus by2 equals to a cosine x1 plus b cosine x2. Now, do you think number 1 and number 2 are same to each other? They are not the same, right? Therefore, it is nonlinear. So 1 does not equal to 2. Therefore, they are nonlinear. Or this equation or this system is nonlinear. Now part B to check is it's stable, to check the stability. So basically we'll replace every x by constant is called m, every y call it by r. So basically y of t will be as r equal cosine of m. Now whatever the value is m when it is bounded, since it's cosine of m, so as we know, the cosine is bounded between -1 to 1. So therefore, the output will be bounded, will not go to infinity. There, r will belongs to the interval between 1 to 1, so it is stable. So basically, if there is nothing will go to the infinity or nothing will be indefinite, then it is stable. Now, number C, to check if it is invertible. So y of t equals cosine of x of t. Now, can I find x of t? Let's see, x of t equal to cosine of y of t. Now, is this invertible? Can this yield to a unique value, or will give several values? Let's think about this. Let's assume, as an example, as y equal 1/2. So x will be cosine inverse of 1/2, and cosine inverse of 1/2, it can be either 60 or negative 60 degrees. Is this correct? So this yields to two different values, not unique. So we can't know exact value of x, because x should be unique value. Basically, it's non-unique, not unique. So we will say it's non-invertible. Non-invertible. Okay? So this is an example of non-invertible, even though there's a way to find x, but the thing is not unique value. Now, example number 4, y of t equal x squared of t. Since it's x squared, of course, we will say it's non-linear, but let's prove this using the analysis that we used to do. So number 1, we'll use like part A to check is it linear or not. Number 1, replace every x by ax1 plus bx2. This yields to ax1 plus bx2, all of it squared. Number 2, y1 equal x1 squared, y2 equals to x2 squared. Therefore, ay1 plus by2 will be ax1 squared plus bx2 squared. And number 1 and number 2, they are not equal to each other, right? Because the square is in number A for all of everything, while the number B is different, so the equation 2 is different. So therefore, it is non-linear. How about the stability? The stability, replace here we have y equal to x squared, replace y by r, x by m, r equal m squared. So if we substitute m, any number, not infinity, of course this will yield to r to be a finite number, right? So if m is, for example, 10, then r will be 100. There is no value, it will not go to infinity if you substitute just a number, a real number, but without going to any infinite number. So it is stable because it is finite, it will not be infinite. Okay? Does this make sense? Part C, to check is it invertible. So we have y equal x squared, therefore x equal plus or minus the square root of y. Right? Now, examples. Assume y equal 25, therefore x equal plus minus 5, right? Which is not unique. Since it's not unique, we will say it is non-invertible. Non-invertible. Okay? So, again, non-invertible means not unique. Now, question number 5. Y of t equals t squared times x of t. Let's see, is it linear? The first thing to check the linearity. So here number 1, substitute every x by ax1 plus bx2. This yields to be t squared times ax1 plus bx2. Now number 2, which is, how about y1 and y2? y1 equal t squared x1. y2 equal t squared x2. While ay1 plus by2 equals to at squared x1 plus at squared x2. try to take t squared as a factor, it will be t squared ax1 plus bx2. So since equation 1 and equation 2 are the same, equal to each other, therefore it is linear. So we will say equation 1 equal to equation 2, therefore it is linear. This system is linear system. Now still our number B, to check the stability, we have y equal t squared times x. So replace y by r, t squared times m. Now, is this stable or not? T, we said m must be non-finite, not infinite, which is finite. Now, t is not necessary. It can be finite, it can be infinite. So as t goes to infinity or with time, as t goes to infinity, yields r goes to infinity. This means unstable. Because this is with time. So it will be increasing with time, increasing with time, increasing with time. Imagine like this is like as a motor speed. Increasing with time, increasing with time. This will be accelerating, it will go over the rated speed, then this might affect on the motor or might damage the motor. Because this is with time. Then therefore it's unstable. Again, the only finite thing is m. Make m finite. If m is finite, is there a way to be infinite? Yes, it can be through t. When t goes to infinity, it can be infinite. Now number C, to check the invertibility. So we have y of t equals t squared x of t. Now we need to find x of t. Therefore, x of t equals to y of t over t squared. Now, does this mean invertible or not? We can find x of t for all of the values except when t equal to 0, right? Because when t equal to 0, it will be infinity. So we have a problem when t goes to 0, this yields x goes to infinity, which is undefined point. Therefore, we will say it's non-invertible. Okay? So you need to know all of these type of checks. Now the last question is 6, which is y of t equals x of t times u of t. Remember, u of t is the step function. And let's check, is it invertible or non-invertible? Or first, I'm sorry, is it linear or not linear? So number 8, when x goes to ax1 plus bx2, this yields to be ax1 plus bx2 times u. Now, number 2, when y1 equal x1 u of t, y2 equal x2 u of t. Therefore, we will say ay1 plus by2 yields to ax1 u of t plus bx2 u of t. So let's take u of t as a factor. This yields to ax1 plus bx2 u of t. Now look at equation 2 and equation 1. Are they equal to each other? Yes, therefore it is linear. So 1 equals to 2. Yes, they're linear. Let's go to part B. To check stability, we have y equal to x of t, u of t. Let's substitute y by r equal m times u of t. U of t is a step function, so how the function looks like? It's actually r equal to m when t larger than 0, 0 when t is than 0. So as a result, is this yields to infinity? No, it will not go to infinity, therefore it is stable. Now part C, to check is it revertible or not, or is it invertible. So we have, again, y of t equals to x of t times u of t. So we need to find x of t, which is y of t over u of t. Now, when t larger than 0, this equals actually to y of t when t larger than 0. When t less than 0, y of t over 0 equals to 3. So we will say it isn't, of course, it is not invertible. Is this correct? Any question about these 6 questions? Let me give you a few seconds to write them, and we'll go to the next topic. So remember our targets to get LTI system, which means linear time invariance. So we know what is linear time invariant. We already discussed this in the last chapter, but let's just a quick review to recall what's time invariance. So for any x of t system, it will give you y of t. While if you make x of t minus tau for that system, so it will give you z of t. If z of t equals y of t minus tau, then it is time invariance. If not equal y of t minus tau, then it will be time variance. Okay, recall how to check this. Recall, check time variance and time invariance, which is basically replace x of t by y of t, or procedure. Step number 1, replace every t by t minus tau, or t0, whatever you call it. Or then step number 2, replace every x of t by x of t minus tau. If 1 equal to 2, then it is time invariance. If not, then it will be time invariance. Recall this example. Y of t equals to x of t plus 2x of t minus 1. So according to our procedure, step number A or 1, whatever. So replace t by t minus tau. This yields to be x of t minus tau plus 2x of t minus tau minus 1. Step number B, replace, here we replace t by t minus tau. Replace step number 2, replace x of t by x of t minus tau. Then this yields to be x of t minus tau plus 2 x of t minus tau minus 1. Now, since A equal to B, therefore, since yes, it is time invariance. Okay? Any question? Let me go on some textbook problems about checking time variance or time invariance. Problem 2.1b. So y of t equals 3 sine t times x of t. We need to check is it time variant or invariant. So step number A, which is replace x of t by x of t minus tau. this yields to be 3 sine of t, x of t minus tau. Now step number B, replace every t by t minus tau. This yields to be 3 sine of t minus tau, x of t minus tau. So you will see the difference here, x of t minus tau, while here sine of t. Then therefore A will not equal to B. Then it is time variance. Okay? Now problem 2.2e. So y of t equal x of t u of t. Number 1, which is replace every t by t minus tau. Whatever, if you mix between which one first, that's fine. X of t minus tau. This yields to be x of t minus tau, u of t minus tau. While part B, when you replace x of t to be x of t minus tau, this yields to be x of t minus tau times u of t. So you will notice the difference in u of t or u of t minus tau. Therefore, A will not equal to B, then it is time variance. Okay? In another example, assuming y of t equals 3x of t plus 2, then let's try to substitute x of t then here equals to alpha brackets. Substitute first thing t to be t minus tau. This yields to be 3x of t minus tau, x of t minus tau plus 2, and for part B, replace every x of t by x of t minus tau. So this yields to be 3x of t minus tau plus 2. Since A equal to B, then it is time invariance. Okay? Any question? Now, let's discuss on, again, LTI system. So we mentioned this a lot, LTI, linear time invariance. So this linear time invariant, these systems are important and very useful in real life. So many applications that we have, they are based on linear time invariance, and you will use this a lot later in communication systems and wireless technologies, and even in computer systems as well. So those are very important and very essential for you later for the future courses. So now we will learn the tools, but without going to the application, just the tools. Like sometimes the math about this, or sometimes like the analysis, how to do this kind of analysis. But you will not see a lot, I think like a lot about the practical things. You will see like more as math. It looks like when you learn like calculus or differential equation, then when in the next course, you will go to the circuit analysis, then you will use the tools that you use in math or differential equations, and you used it in circuit analysis. So this is also the same thing. This is just basic course or introduction or course, so you will use these tools later in the future courses. So again, this is important. Understanding this very important because you will use it later, and you need to make sure to be up to date with this course, because again, it is not easy. In LTI system, we will assume we have x of t. Here is LTI system. So the outputs will be y of t. Now, x of t can be any inputs, but let's discuss some special cases, some special inputs. So we discuss some functions here. So we have some special functions like delta of t, U of t, R of t. Step or step, ramp, step, and delta function. So we know these functions. Why we discuss these functions a lot? Most likely you will also, as you will learn this later, we used to these inputs as kind of tests to test the system if the system is working or not. So we can test that system by impulse response or input response or step response or ramp response. Also, you will use this later in control system course as well. Then these type of 3 inputs again used to test the system. Then if the system is functioning well, we can apply to real life. So all of these type of inputs again important to test the system. Then most likely you will see it later when you do the control technique for anything or build any system. Basically you will make step number 1. We test my system using delta inputs. Then step number 2, test my system using step inputs, then using the ramp inputs. Then after that, that's how we validate our work. So most likely you will see technically or when we do the analysis to prove the things by testing these type of inputs. Okay, so let's talk about number 1 when we have the input is delta of t. So when the input is delta of t with the LTI system, the output, instead of mentioning it will be y of t, we will divide it by h of t. Just as simplification, so we can realize whenever we see the h, this means the input is delta. In this situation, this type of system will be called impulse response. Such that here again, every x has been replaced with delta, y has been replaced with h. So we'll call it impulse response. Such that, what's the response? H of t. H of t is the response to inputs delta of t. So you have the inputs h, or you have the input delta of t, the output will be h. It looks like you have a system here, like as a box. Then you inject delta of t. Then you monitor what's happening. So what you will see the output, h of t. And it's called impulse response. So how about if we used u of t? U of t, here is LTI. So I injected u of t. The output will be called as u step of t. U substep. Then this is called step response. Step response, which is y step, is the response to inputs u of t. Then the same thing for number 3, r of t, which is the ramp, will be called ramp response. So here is r of t, the output is called y sub ramp of t. Then it's called ramp response. Basically, the inputs or y ramp of t is the response to inputs r of t. Okay? So now, whenever we talk about a word response, this means the outputs. While whenever you see y function, or step function, this is the inputs. So when I say step function u of t, delta function delta of t, ramp function r of t. But whenever I say step response, this means the outputs when I make the input y of t. When I say the ramp response, the outputs when I make the input is ramp or r of t. Impulse response, the output when I make the inputs as delta of t, or sometimes we call it impulse function. Delta of t can be called delta function or can be called impulse function. So again, most likely these three inputs are very common to test our LTI system for validation, to make everything is fine. Most likely we use in real life impulse and step more than the RAM. But all of these three are important. Then now I have my own system. I injected delta function or injected delta or input U of t or R of t. But in signals or in systems, actually, we need to test what the output will be. So sometimes we have a system, put it, then you will see the behavior. But sometimes this can be unrealistic, which is, if I don't know what's going on, how can I expect maybe this might be go to unstable, or this will be something might be dangerous or will affect the system. So the first thing that we need to have for any system is to model it. How can we model the system? Is maybe through the differential equation, or do it like any relation between input and output, so we can do a model. So whenever we have, let's assume we have any box, we have inputs and outputs. So we need to find a relationship between input and output to find the model of the system. Okay, that's my first step, modeling. Second step, tests the system, tests inputs. So I will test the inputs. So I will test delta of t, U of t, R of t. Or in other words, impulse response C, the impulse response C, step response C, run response. So that's my next step. So I need to do this not in hardware, and to do this in equations by using the system equations. So I need to see how was the output Y of t. So test inputs with equations or theoretically. If everything goes well theoretically, then I'm ready to apply this in experiments. Apply experiments. Okay? How can I apply, or what should I do again? You have a model, then you can test the inputs. So you need to make sure for any system to have an expected behavior. So you can say, if I did this, I predict to get this thing, or it's supposed to have this kind of output. Then you can monitor your output to make sure that to guarantee that you will get the outputs. Okay, let's go to one example in real life, which is in how to get the outputs, or how first to model the system, then how to test the system with different inputs. That example will be long, so it will not be done today, maybe next lecture, or even in Friday lecture. Okay, so here's an example, which is the RC circuits. RC circuit. In RC circuits, AC RC circuits, you have a source, and here you have a resistor, then a parallel capacitor. That's it. Then we put the outputs, which is the voltage. We need to measure the output. So here, plus minus the output. I'm going to assume the output as Y of t. I'm going to assume the input as X of t. What's the system? The box of the system to include overall the system, this one, RC. So this is the system. So my target is to make it, to find the equivalent relationship such that this is X of t, this is Y of t. Here is the model that I have, system model. I need to model the system so I can reach this. How can I do the modeling for this? Input is voltage, output is the voltage of the capacitor. Okay, how can I do the model? Using circuit techniques analysis. Look at this one. Let's assume a current direction and some voltages. So I will say this is I. I'm assuming the current going out from the source. Then I will assume this is plus minus VR, and here this is plus minus VC. Okay? Or it's the same as Y of t actually. There is no need to say so. Same as Y. Okay? And I will keep flowing. I will not go here because it's open circuit, so I here will be 0. Okay, you know this from the circuit, right? So it's like single loop. Now, how can I do the calculation? Again, it's AC, so we're going to make the lower cases. Here's I, again, it's AC, and we'll make the lower cases. Let's do KVL at this loop. KVL, loop 1. Let's do it from the left bottom corner, then go clockwise, and let's do it in the basic way. So let's do it, it will be as negative x of t plus VR of t plus y of t equals to 0, right? Then let's substitute VR of t as I times R. So it will be negative x of t plus R times I of t plus y of t equals to 0. Now, my target is to make inputs relation of outputs. So we have here the outputs. I have the output here. I have the input here. R is constant, that's fine. But my concern is I of t. I mean, I have only one input in this system. I didn't have two inputs. So I need to get rid of I of t. I cannot model my system when I of t exists. How can I remove I of t? Let's look at the circuit to see, is there any simplification for I of t? Look at the circuit. I need to remove I of t from the circuit. Is there any equation to govern I of t that's linked either to inputs or to outputs? To the inputs, I don't think it can be a good idea. Let's look at the outputs. Is there any relationship between the currents? Because here I keep flowing. Here. Between I and the outputs and the voltage of the capacitor. Is there any relationship? Yes. We know I equals C dV by dt, or dV by dt, which is the time derivative of the voltage. Is this correct? Equal. Here is the capacitor. Here is the currents. Plus minus, here is the voltage. So I of t equals C dV of t by dt, right? Now in our target, or in our analysis, I of t equals C, the term derivative of the voltage here, it's the output, it's the term derivative of y of t. Now let's substitute this in the equations. We can substitute this here. This yields to negative x of t plus R times C dy of t by dt here plus y of t equals to 0. Okay? Now, let's move x of t to the other side. So it will be as RC dy of t by dt plus y of t equals to x of t. Okay? Now I have everything written in inputs and outputs with constants. So we prefer in the differential equation to make the higher order with factor 1. So let's divide by 1 over RC dy of t by dt plus 1 over RC y of t equals to 1 over RC x of t. And this is first order differential equation, right? First order ordinary differential equation. Most likely, we used to donate 1 over RC equal to tau. We used to do this tau of the capacitor, which is the time constant. So it will be as dy of t by dt 1 over tau c, I'm sorry, it's tau c. Tau c y of t equal to tau c x of t. That's for the RC circuit. Then now I'm done. That's the equation that I need to model my system. So the overall output will be as, here is input x of t. That's the box that I need to do my model. Here is y of t. So it will be as dy of t by dt plus tau c y of t equal to tau c x of t. Now, with this, I can guarantee my system, or I can guarantee that this is the system that we have, which is the model system model for RC circuits. After testing this, you will realize it is, after testing, you will realize it's LTI system, linear time invariance. So what should I do next after I model this? The next thing, I'm trying to test the inputs, test the system to do the input. Now, test inputs. So basically, I would say we need to test impulse response. Next thing, we'll test unit step response, unit response. Then ramp response. That's what we are going to do. So we need to test all of these to make sure, or to see the expected behavior, to see how the output will look like. Once we get the outputs, then we can try to apply this in real life to see how we can with different type of factors. So that's most likely that's what we need to do. So we need to apply for this system 3 different things. Let's do the impulse response first. Impulse response. For impulse response, every x of t will be replaced by delta of t. Every y of t will be replaced by h of t. So the differential equation was dy of t by dt plus tau c h, is it tau or tau? Okay. Let's do some correction. I apologize about this. Anyway, we need to be consistent. So R times C will be tau. So everything will be 1 over tau, 1 over tau. That's my correction. So everything will be 1 over tau, 1 over tau. I apologize about this. Okay. Correction, 1 over tau. Now, so it will be here as 1 over tau y t plus 1 over tau x of t. This is the original equation. Let's do the replacing by replacing y by h and x by delta. So it will be dh of t by dt plus 1 over tau c h of t equal 1 over tc delta of t. Now, how to solve this type of differential equations, especially we have a delta function. It's not like, as we know in differential equation courses, it will be harder because we have delta function. So how can we use this? We will use a method that's called, we will use integrating factor method. For doing this thing. So basically, integrating factor, our output is h of t. So we will just multiply by exponential e over t over tc. Now, the next thing we will do the derivative, d by dt of that expression, which is h of t times e power t over tau c. So the derivative will be as the derivative of the first one times the second one. H of t times the second one, e over t over tc, plus the second one times the derivative of, the first one times the derivative of the second one, e power t over tc. Then it will be as, after doing the derivative d by dt h of t times e power t over tc plus h of t, the derivative of the exponential is 1 over tc times the exponential itself, tc. So what I'm going to do is I'm going to take e power tc as a factor. So this yields to the derivative d by dt of the exponent, the term h of t e power t over tc equals e power t over tau c as a factor. Then we have d by dt h of t plus 1 over tc h of t. Okay, how can this be beneficial to us? Let's go back to the original system. It is d by dt h of t plus 1 over tau c h of t equals 1 over tau c times delta of t. Let's make a comparison between this part and this part. You will see they are the same. So as a result, I can say d by dt h of t e power t over tc equals to be e power t over tau c times 1 over tau c delta of t. So here we make it simpler. Okay, so what? We call that property, now we have this, we have delta of t times e power t over t cell. So we call x of t times delta of t equals x of 0 times delta of t. One of the properties that we did a lot. So how can this be beneficial to us? We have the constant term, or we have e power t over tc times delta of t. This means e power 0 over tau c times delta of t. And e power 0 means 1, so it will be as delta of t. So as a result, this yields to d over dt h of t e power t over tau c equals to 1 over tau c times 1 times delta of t. Okay? Let's use this method. So now, since we have this result, which is more simplified, let's do the integration. Do integration to remove the derivative. So by doing the integration between 0 to t, d by d tau h of tau e power tau over tau c dt equals 1 over tau c, so the integral between 0 to t delta of tau d tau. So let's stop here. In the next lecture we will do the integral to find the steps, the inverse response.